Swayam Prabha. Digital India. Educated India.
Welcome to the NPTEL online certification course on structural systems in architecture. We are in the module 2, that is the strength of material is our topic of concern of this second week, and we are in the last lecture on this topic, the module 2, and this last lecture is on the SFD and BMD special cases. We have discussed the SFD, the shear force diagram, and BMD, the bending moment diagram, in the last 2 consecutive lecture. And in this last lecture, we are going to sum up and we will give you some kind of the discussion based on some of the special cases. And this concept of this particular lecture is with we have to first see that what is the relation between the shear force and the bending moment, and then we have to see a concept of the point of contact flexure, and what is that, and what is how it is important from the structural the engineering point of view. We have to see that, and then we have to also see the some of the cases of the one side and the two sides overhang beams problem, and then finally we will see the loading diagram from SFD and the BMD. Practically this last one will be discussed as a purely academic point of view for any kind of competitive examinations or so. So, the learning objective of this particular lecture will be we will differentiate and relate between the BMD and SFD. Perhaps at this particular point you can differentiate between the BMD and the SFD, but we have to now relate these two mathematically and conceptually, and we will illustrate the actually this is a slight spelling mistake, it is not overhand but it is overhang beam, and we will also going to relate the loading diagram from the SFD and the BMD. So, the relation between the bending moment and the shear force diagram. Let us see, this is a cantilever beam and it is having a UDL of omega or W over a length of span length of L meter. So, I take as distance from the B, that is the free end, and let us first compute what is the shear force. And shear force is a linear, as you all know, it is going with a F equal to minus omega or W into x, because at this particular point the total load is this load is your W into x. W into x is the total load. If you increase the amount, the distance, the x is increasing and gradually increasing. So, this is it is a linear diagram of the shear force. Now, what is the bending moment? Bending moment is parabolic, as you all know. Last lecture we have discussed that one thoroughly. So, at this particular moment, again let me show you, if this is the W, so the W is actually acting as the total load as acting as the W into x, and this distance is your x by 2. So, the total moment is W into x into x by 2, so that is W into x square by 2, and this is negative because it is a hogging kind of a moment. So, this is mx at any point x, it is W into x square by 2. So, these two are we have discussed in the last 2 lectures and we computed that. Now, let us see, if I differentiate the bending moment expression, that is the bending moment expression is W into x square by 2. If I put the differentiation with respect to x dmx dx, then what we found that this 2, the power 2 comes here and x by 2 remain, and this 2 and 2 goes, and this is W into x, that is fx. So, I can say that the differentiation, the first order of differentiation of bending moment with respect to s is nothing but the shear force. That is the relation between them. That is the relation between them. And again, if I go further, if I differentiate the SF expression, so SF the shear force expression is this, then Fx equal to minus W into x. If I again differentiate that with respect to x, then I will, this x will go out, because x is go out, and then this because as you know, the if there is some x to the power n, the function is something like that. So df, this will be, this n comes and this is x into n minus 1. So from this particular fundamental principle I can evaluate these two. So this is minus W is nothing but the loading intensity. So finally we may say that the differentiation of bending moment is shear force, and the differentiation of the shear force is nothing but the loading intensity, or second order of the differentiation of the shear force is bending moment is the loading intensity. We will discuss this because not because of make your life in complex, but you need to know this, because if you want to find out the further some of the principles of the deflections and all, where we need some amount of this differential calculus or so, but that is very simple. Those are come along with this x to the power n kind of category. No trigonometric or some complex logarithmic functions in this differentiation. So again you see, if you just see that how it is going to validate in a case of the simply supported beam. So I have a simply supported beam overall UDL, and so the reactions are WL by 2, WL by 2. I have taken a section x from the left end at a distance x. So the bending moment expression is WL by 2 into x, which is this, and Wx square by 2, that is minus this, and Fx is WL by 2 minus W into x. So that is simple. If you have any doubt, you can go to the earlier lecture and you see those two expressions. And if I differentiate this one, that is the differentiation of this bending moment, if I do, then this WL by 2, this x vanish, and this 2 comes forward and this 2 goes. So this will be the expression which is equal to this expression. So this is Fx, and if I again differentiate this, so finally it is the loading intensity, because this expression, if I differentiate, this is a constant term which is going to be 0, and this differentiation x vanishes. So this is minus omega or W. So W is nothing but the loading intensity. So next let us discuss another very interesting thing called the point of contact flexure. This is a simply supported beam, and if I draw it, or if I have a beam something like a cantilever portion and a simply supported portion. So if I just push this particular support a bit inside, so this is a simply supported beam and this is a overhang kind of a beam, one side overhang kind. This is called a overhang beam. There can be a two-way overhang beam also, where I can push this also towards right, and I have a cantilever portion here and cantilever portion here, and in between there is a simply supported portion. So this is called a two-side overhang beam. So let us in this case let us take a the one-sided cantilever overhang beam. So the simply supported span is 4 meter and a cantilever span is 2 meter, acting at a monolithic kind of a construction or a monolithic kind of a beam, and there are some point like A is this end, the simply supported end, C is the free end, B is another simply supported internal point, and D is the mid between the A and B, and this is experiencing a load of 10 kilonewton per meter, and this 4 and 5 meter are there. So I first found the reactions found. If you take the 4 RB, why 4 RB? I am taken the moment at A equal to 0. So this length is 4 into RB this way must be equal to entire load because of this 10. So entire load is 10 into 6 acting at a point at 3. So 10 into 6 into 3, that is 180. So that means this is 45 and this is 15. So by virtue of this I can find out the reaction, and also I can find out the extremely sawtooth like the shear force diagram. Let me explain this shear force diagram also. It is 15 goes up because it's 15 reaction. Follow my finger, this particular point, green pointer. Now, if you go 1 meter, you lose 10. So, if you go 1 meter, you are now 5, like that. So, after 1 meter, you are 5. So, again some meter it is 0, and if you go like that, after 4 meter, you lose 15 minus 40, that is your 15 minus 40, that means you are in somewhere here is it is in 20 plus 25 is 45, it is this up, and then again it is 0. So, like that, if you see that this is 1.5 meter, because 1.5 meter this the shear force is equal to 0, because if you go 1.5 meter, you will be having almost about 15 kilonewton go down. So, this plus 15 and this is minus 15 is give you 0. This will be if you go again further 2.5 meter, though this has to be actually 25 and this has to be your 20. I am just sorry, I am just I will send the PPT, the right PPT like that. This is a little bit of a problem. So, this is, so I will read put this again. So, this has to be 25 and this has to be 20. You read it as it, I will upload the right PPT in the forum. So, it goes like that. Then this is the shear force is 0 at this particular point at 1.5 meter, because it is started with 15 and after 1.5 meter is lose 15. So, shear force is equal to 0. This point, please remember, this is important point at 1.5 meter from the left support. This point you must remember. Next, now let me take the bending moment one section by other sections. I am taking a bending moment from C. So, at any section from C, the bending moment is 5x square, because it is 10 into x by 2. So, if it is so, at C it is 0 because x value is 0, at B it is 20 minus 20, of course, it is because it is the MB equal to 20, because the value of x equal to 2. Now, at C, if I take a section x, which is after this particular 45, my expression is 45 minus x by 2 y. Now, this section this is my section of interest. So, this length is x minus 2, because this entire length is x and this is 2. So, x minus 2 minus this 10 x square by 2. So, this is the total expression. If you open it up, you will do a total expression, and now also you can find out the values of the C, the moment at C, which is again come back to 20 by if you put the values of x equal to 2, and if you put the value x equal to 4, x equal to 4 means at the midspan at the D, you put x equal to 4, so you will get as positive 10. This is positive. Remember, this is negative. So, this is negative diagram, this is positive diagram. I will clear my write up and let us see once again. So, this is my MD, moment at D, and this is my MB. This starts from 0, goes parabolic and then again increase and then goes like this, again it is going to be 0 at MA. Now, let us see what happened at a distance x from the C. The expression is this, the last slide we have x. Now, we put this the differentiation of the bending moment with respect to x. If I do, then this is 45 in minus this 2 goes here. So, 5 into 2 10x, this 90 goes out because it is a constant. Now, if I put this equal to 0, that means 45 minus x equal to 0. The dmx dx equal to 0 means where the slope is equal to 0, and I get the value x equal to 4.5 meters. So, that means from here at a 4.5 meter, 4.5 meter, this dmx dx equal to 0, that means the mx is maximum, right. Any mathematical expression whose differentiation is equal to 0, at that particular point the curvature is equal to 0, that means it is either maxima or minima. Here it is maxima. So, at x equal to 4.5 equal to 0, at x equal to 4.5, that means how much it is from here? the total length is 6, that means 1.5. Please remember, in 1.5 what we have seen, the shear force is equal to 0. So the bending moment is maximum where the shear force equal to 0. So M max, to find M max, what I have to do is that I have to put the x equal to 4.5 in this equation. So 45 into 4.5 minus 90, 5 into 4.5 square, that is 11.25. So at this particular point at 4.5 or 1.5 meter to 4.5 from the right hand end, this is the max, the maximum bending moment occur. That is very interesting. So where shear force, and this particular point, if you remember, the shear force was actually going to 0 at this particular point. Now by taking a section x, and this is the equation as I understand comes over here, and I put the mx equal to 0, I want to find out where this 0 bending moment is. If I put equal to this 0, I get a quadratic equation like this, x square minus 9x from here, and I can solve this quadratic equation and can find out x equal to either 6 meter or 3 meter. So this is my 3 meter, and actually this is again a mistake, this has to be 3 meter, because this is 2 meter, how can this can be 1.5 meter, this is 3 meter. So at a 3 meter this has to be equal to 0. So this point is called point of counterflexure, because this point is called the point of counterflexure, because bending moment is 0 here and bending moment change sign. Why bending moment change sign? Because at the right side of this particular point, bending moment is negative and the left side of this is positive. So this is hogging and this is sagging. That means this part it is hogging and this part it is sagging. So the beam is bending like this, it changes sign, So that is why this point is called point of counterflexure, and this is very important, because if you want to see the reinforcement and all these things, there will be a change, the hogging and sagging changes, that means the bending moment is 0 over here. So I can say whatever I have drawn over here, I have again written over here, at this particular point this is the tension bottom, that is the sagging, and this particular point it is tension top, hogging, because this is entire portion is negative and this entire portion is positive, right. So it will be bent like this. This is the hogging kind of a bending and this is the sagging kind of a bending. So this will be the usual case. So in this case, just last one, let's see this, whatever we have sum it up, I will have sum it up like that. The bending moment is maximum, the point where the shear force equal to 0. Please remember this point we have marked as 1.5 meter. And second point is point of counterflexure is a point on bending beam where the bending moment is equal to 0, and we found this point as 3 meter. So let us go to the two side overhang beam cases. There are 4 such cases I have going to describe with you. The overhang beam is of the total length of the beam is 8 meter. This L is equal to your 8 meter, and the overhang length is, suppose this is the overhang length, which is your A, and this entire length is your L. This is 2 meter. So the A by L is equal to your 0.05, and as you know, this is total length is your 8 meter and the total load is your 10 into 8, 80, and it is equally distributed. So the 40 and 40 will be your reaction. So the MA and MB I can find out, it is very it will be symmetrical, because this MA will be 2 into 10, 2 into 20, 10 is 20 into the 1, that means equal to minus 20, and ME also I can find out by 40 into 2, 40 into 2, why? Because this is, again let me clear it, at this particular point this is 40 into 2. So this, and this entire length is how much? This is 4. So 10 into 4 into 2, that means equal to 0, that means at this particular point is 0. So it is negative, and this is the bending moment diagram BMD. Whereas the shear force diagram is very interesting. This is from here it is 0, it goes 10, negative 10 by per meter. So, per 1 meter if you go it is minus 10, again it is minus 20, and then get a push of 40, so 20, and then get a positive 40, again goes like that, it end up with 40 minus, so plus 20 minus 40 is minus 20, again I get a push up 40 and then again goes down. So, like that I get the bending moment diagram. Now, in the next case what I have done is that here you see the A is 2 meter and the L is 8. Here I make the A is 1 meter. So, I increase the span length. So, now as you see this 4 meter is increases to 6 meter over here, but the reactions will be equal because there is no change in the loading and no change in the overall length of the beam. So, now I have computed the MA and MB. The MA and MB will be minus 5 because it is now 10 into 1 into 1 and half. 10 into 1 is the total load and the distance is 0.5. So, it is 5. This is minus 5, and also I have computed at the mid section how much is the bending moment. So, this is 40 into 3 now. You see 40 into 3 minus 10 into 4 into, because 10 into 4 is the total load and it is acting at it 2. So, then it is plus 40. So, this is positive, this is negative, and these are the point of counterflexion. So, it will have a kind of a moment like this, or this particular point is the hogging, this particular point is the hogging, and this particular point is the sagging. So, the beam will bend like this. The earlier case this entire portion is the hogging portion. So, this is something like this, it will bend like this. The third case, you see the third case what happened, I put the, instead of the initially it was 2 meter, 1 meter and then 3 meter, then I push it little further inside. So, the overhang is very high with compared to your internal simply supported portion, but this reaction remain 40 because total length of the beam remain 8 meter, no change in the loading. And if it is so, I can find out again the MA and MB, which is 45 because it is 10 into 3 into 3 and half. So, 45, and at this particular center it is 40 into 1 minus 10 into 4 into 2 to the minus 40. So, it is also minus. So, entire portion is hogging. So, and this hogging is tremendous kind of hogging. So, the beam will be bent like this, not a flat kind of hogging, it is a huge kind of a bending. Now, here also you can see your shear force diagram also changes. It is 0 and per meter if you go it is 10, so it is 30, 30 plus 40 is 10, it goes like that, it is only 2 meters, so it goes to this minus 10, again you get push of 30 and then again 30. If you go to the earlier one, so it is again it is 1 meter, so it is 10, then push a 40 and then goes 30 and push a 40 and like that. So, you can have the sheet saw teeth in different kind of sections. Now, let us go to the fourth one. In fourth one, I put the A equal to a peculiar number 1.656 meter. See, let me go back a bit. So, here if it is 0.25, A equal to 0.25, then you will get 0 bending moment at the center. If it is less than 0.25 A by L, this ratio, you will get a positive bending moment at the center. And if it is greater than 0.25, then again you will get a 0 or greater than this thing, you will get a negative bending moment at the center. Now, if it is A is 1.656 meter, that means, and the total length remain as same 8 meter, then A by L is your 0.207, 0.207 is in this is less than 0.25. Less than 0.25 means there will be some positive bending moment at the center, and if you compute this reactions will be 40, there is no change. So, at this particular point MA and MB, it is 10 into 1.656 into 1.65 by 2, that means minus 13.7, and at the particular section, central section, this is 40 into 4.688 by 2, minus 10 into 4 into 2, that means 13.7. So, what happened? This positive bending moment, the highest positive bending moment and the highest negative bending moment are now equal. So, it is a very symmetrical kind of a case where you can have a very similar kind of the reinforcement or so in future we will discuss. This is the one of the. So, if you can have the overhang is 0.207, I mean almost 20% overhang with respect to the overhang length of the with respect to the total length of the beam, then you will get some benefit. You do not have to deal with the reinforcement. It will be a similar kind of reinforcement. Some portion will be in the bottom and some portion will be in the top. In the hogging portion will be in the top and sagging portion will be in the bottom. So, we will discuss further the advantage of this kind of a section afterwards. So, loading diagram from the SFD or BMD. So, this we will discuss for sake of some the academic interest, some questions in the GATE examination or some other the examinations in the government examination, competitive examination, sometimes it comes. So, suppose this is a beam, simply supported beam given, A and B are the end, simply supported end, and this is the diagram. So, I know in this, then you have to find out the how is the loading diagram, the reverse process. So, this is the beam. So, I know this is, so that means 28 means this is the reaction is 28, and this is 37 means this reaction is 37, right. So, it goes 28 and then it is dropped by 3. So, that means definitely there is 25. Some force is there which actually of 25, because it goes to 28 and suddenly it comes here 23, that means this portion is 25 and this portion is 3. So, this 25, and again it is nothing over here. So, I cannot expect any load, and if it is something like this goes like that 37 and this is 3, then I can say this is 40, and 40 plus 25 must be equal to 28 and 37. So, let us see. So, this is 25 and 40 will be your this diagram. So, from the SFD you can easily find out from the step wise you can easily find out the first try to find out the what are the reaction load or so, but here I have again done a small mistake. These reactions are not 30-30, these reactions are of 28 and 37. Suppose this is a other one, it is a BMD is given, this is the BMD, and I have written that this much is the parabolic portion, this is a straight line portion, this is another straight line portion. So, 60 straight and then a parabola and then a 60 2 meter beam, find out the loading diagram. So, I know that if this is a parabolic portion there must be a UDL, and of course, there may be pointed load or may not be pointed load, that is different because I do not have the shear force diagram, but as I am sure there is a UDL because that will give you a kind of a, and also I know that this is a symmetrical diagram. So, the reactions also will be symmetrical, and this reaction whatever may be the reaction R into 2 must be equal to 60, because then only I get a 60 over here and this is straight line. So, I will first find out like that from the symmetry. If I assume that there is a UDL and this is P, first you have to actually conceive this one, that this has a UDL inside and there are maybe a P pointed force, pointed load, and both has to be equal, otherwise this symmetrical diagram cannot come, it cannot be P1 and P2. So, based on that I have drawn this diagram, but I do not know the values of P and W, but I know that this particular total amount of force, and this is 30, this total amount of force is, this is 30 because this 6 that I told you, this the reaction R multiplied by 2 must be equal to 60, that means the reaction is equal to 30. So, this is 30, this is 30. So, this P into the half of this W into 2 is 1 meter, this is 2 meter, the W into 1 must be equal to 30. So, the P is equal to your 30 minus W. So, the half of this portion load must be equal to this reaction, and half of this load equal to this reaction. Half of this load is P plus W into 1 meter must be equal to your 30. That is the thing I have written over here. So, P equal to 30 minus W. Now, further I have to actually equate the mid-span moment. So, how much is the mid-span moment? That is 65. So, I can write down the mid-span moment is that, equating the mid-span moment with 65, it is 30 into 3 minus P into 1 minus W into 1 into 0.5. So, I did that and I replaced the value of P by 30 minus W. So, rearrange this. So, I got W equal to 10 kilonewton per meter, and placing 10 over here, P equal to 20. So, this P equal to 20 kilonewton and W equal to 10 kilonewton per meter is my final answer to this question. So, I have taken reference of these few books, and I have concluded with that the differentiation of bending moment expression gives the expression of the shear force. The point of counterflexure is a point where the bending moment is 0 at 0 and it's changed its sign over there, and the loading diagram can be established from the bending moment diagram and the shear force diagram as well. So, that is the end of this particular lecture, and we will move to the next lecture on the module number 3 as the structural mechanics. So, I have two homework for you. So, draw the shear force and the bending moment diagram for this overhang beam I have given over here. So, you have to draw that, and I have given the UDL also, the pointed load at the free end also, and also I have given a homework like that very similar to that, the BMD to SFD. So, the simply supported beam is like this, and it is a straight line portions. This is straight line and this is parabolic, this is again straight line. So, in this portion the bending moment diagram is like this. So, you have to draw the loading diagram and the shear force diagram. Beam is supported at A and B. I think that is all for today. Thank you very much.